Okay, I'll get started. Looks like the bad weather has kept some people, delayed some people, so you'll join us as time passes. So I'm going to continue with what I touched upon last time, which is quantization. I'll just explain how we quantize a one-dimensional and a two-dimensional, and I guess even a three-dimensional signal, how to quantize that. And then I want to give you just like a 2-minute sketch on a couple of results in hypergeometry, which is a geometry of spaces with dimensions higher than 3 dimensions. It turns out it's not particularly hard. It just sounds complicated, but you can talk about 20 dimensions or 50 dimensions, whatever. At least the results I'm going to present here are pretty straightforward. And that will, then setting that aside, I'll talk about the Gaussian channel, which is a modeling of a realistic channel. And then we look at the capacity of a Gaussian channel. So let me start with sort of the easy stuff, which is quantization. So let's consider a signal where with respect to time we have some signal value x. And so this is some continuous signal that we have over here. When you quantize it, what you're going to do is to basically choose certain time periods which are multiples of some basic time period, which is, let's say, t, this is 2t, etc. So all of the time periods are some multiple of the sampling interval, which is capital T. And that is just sampling. What we're going to do, however, in addition to sampling it, okay, which is going to give us a set of real values, is we're going to quantize it as well. So we're going to choose some discrete levels over here. And so this discrete levels over here allows us the possibility of encoding each value over here with a symbol sequence, which is a binary single sequence. It doesn't have to be, and it can be any sequence actually. We don't really care what they are. For example, this would be some symbol sequence. From our perspective, we don't really care what the symbol sequence is. Actually, in some sense, we do care. Okay, what is one thing we should do about choosing the symbol sequences over here? What should we do? Okay, so when suppose somebody says quantize this, a naive way would be to have all these values be going from 0, 0, 0, 0 to 1, 1, 1, 1, whatever, right? But you can be cleverer about it. What should you be doing? Okay, remember it's source coding. Yeah, Alan?
Looking at which ones are more common?
That's correct. You want to find those values that are most common and give that the shortest sequence. Okay, there's no reason why these have to be equal length, right? There's nothing that says they should be equal length. That's just a convention. But it turns out, for example, that most of your values are over here. Then these guys over here should be given values like, 0 and 1. Okay, so you'll have very short encodings of common values. Okay, now of course that's not what we do in practice. In practice, we don't for audio and signals at least we don't do that. For images we do, but that's a different story. I'll come to that in a minute. Okay, so this quantization of in this case a one-dimensional quantity over time allows us to come up with a sequence of symbols, binary symbols over time, and then once you have the binary symbols, we can put that into a channel coder, and that gives us the zeros and ones that are sent on a digital channel. Okay, so that's quantization over here, and that's what I want to explain. So the important point here is that we can talk of any continuous signal. Okay, any continuous signal can then be sent on a digital channel, and the reason we want to use a digital channel is because we're able to recover from errors. We're able to recover from errors because what we'll do, as we'll see in just a moment when we talk about the Gaussian channel, is that we will choose the code words in such a way so that even if there's an error, we can still figure out what was actually being sent. So despite there being distortions introduced by the channel, the code words will be selected in such a way so as to remove the effect of the noise. Okay, and I'll show you that. We'll see that in very great detail in just a few minutes, and that's why digital channels are always superior to analog channels. Okay, that's why you have MP3s and CDs, which are digital channels, and in many ways they're better than the corresponding analog channels, LPs and cassette tapes. Cassette tapes are obsolete, right? Videotapes are obsolete. Why? Because they're all analog channels, gone. Okay, now in doing this, however, we have to be very careful. We have to be careful that if you take the Fourier transform of this, and we have some signal which is going to have, this is not the omega axis, we have some width, okay? Remember that to prevent aliasing, if the width of the channel is W, should make this W hertz, okay, or W radians per second, we need to make sure that the sampling frequency is going to be at least twice that. So basically, we need the 2 pi by t is greater than equal to 2 omega, 2W, right? Because that's the equivalent sampling frequency, and that should be greater than or equal to twice the bandwidth, okay? So we're going to choose t to be sufficiently small. The greater the inherent capacity of the channel, which is of the signal W, the faster you need to sample. And so some people will claim LPs have some intrinsic audio properties which are superior to CDs because they capture this beautiful analog stuff that you can't see. These guys have no clue about Nyquist theorem. Okay, the audiophiles who spend thousands of dollars in very expensive LPs should actually take a course on signals and systems. Okay, and they would save a lot of money. All the money they would spend on buying high-end audio equipment, they should spend on paying professors to teach them signal systems, because they know that the band, your channel, your audio channel, your hearing channel is no better than 40 kilohertz. Even the best audiophiles, not more than 80, let's say 60 kilohertz is the audio capacity. So if you sample at 120 kilohertz, you basically, no way you can detect it. I mean, this is a mathematical theorem. So anything beyond that is just fantasy. So you can tell that to your audiophile friends. At any rate, if we have this W as the limit, which is the limit of the signal or the channel, doesn't really matter. W is all you got, then we know what the frequency we should be sampling at is t. Okay, that's for one-dimensional signals. What about two-dimensional signals? Let's go back to our billboard. So here's a billboard. It has some arbitrary stuff on it, and I want to quantize it, right? I want to send a communication signal. From our perspective, what's written on it doesn't really matter. We want to do it for all possible billboards, okay? All possible billboards. So what are we going to do? We're going to do is we're going to do the same trick where we just divide it up into a grid. A grid that's fine enough so that intuitively there is a frequency corresponding to any signal that's a two-dimensional signal. You take a two-dimensional Fourier transform and you'll have a bandwidth as well. Okay, there's intuitive, we kind of intuitively see that a drawing which has lots of itty bitty, twists and turns has a higher frequency in a smooth curve like that. Okay, there's more signal in there. At any rate, we choose the quantization levels to be close enough so that either they capture all the minor variations or your visual channel, which is what you're seeing it, cannot recognize it, right? So if I show you a 16 megapixel photo and a 32 megapixel photo, you can't see the difference. You just can't, because basically your visual channel is not broad enough to see it, right? So 16 megapixel, 32 megapixel camera doesn't matter. Just buy the cheaper one, okay? Because it doesn't really make a difference. So what we do is based on either the channel or the signal, we choose a grid like this, and now we have a finite set of grid points, right? A megapixel means a million pixels, where each pixel is actually one point over here, and there we just record the image intensity. So we get a two-dimensional system, and then we just read it off like so, and at this point, you've got a digital signal. If we just stop here, what we're saying is all sounds and all images, all sounds, all images, and all moving images, movies, which are just a sequence of images, every 30 milliseconds you show a new image, and your brain is confused, it says it's continuous. Brain cannot, again, the channel is such that, our brain channel is such that anything faster than 30 milliseconds cannot be seen. That's sort of a natural break. So if you show anything 30 frames per second or faster, you'll think it's continuous. You don't realize it's discrete. Okay, so because of this limitation, we can take any continuous movie, still image, or sound, and we can digitize it. And this, in a nutshell, is basically what the digital revolution is all about. Because I can take a sheet of paper, I take a photograph of it, it's a JPEG. At this point, it's digital, right? I can reproduce it if I have sufficient fineness of resolution, I can take any image whatsoever and take a photograph and email it. It's all bits at the bottom, right? And that's Shannon's fundamental contribution. It's all bits in the end. It's all bits in the end. And if you know how to transmit bits, how to manipulate bits using computers, you basically have managed to digitize the whole world. And Nicholas Negroponte, a famous kind of professor at MIT, I'll say kind of professor because he's actually not a professor, it's at MIT Media Lab, which is not quite MIT, and so he's a sort of professor. But he said atoms to bits, that's the major transition. If you go from atoms to bits, if I send this to you by post, it's atoms. I'm sending you sheets of paper. If I send it to you on a network, it's bits. And the major transition of the global economy is from atoms to bits, and it all is happening because of Shannon, because he said, yeah, you know, I can figure out how to convert everything to bits, and then I'll tell you what the capacity of a channel is. And in a minute, I'll show you, he said, what to do with noise, how to get rid of noise. Once you do that, life is great. Okay. So this is just like an introduction to 2D quantization. The actual bits that you generate from doing this kind of thing are too large, right? If you're 12 megapixel camera, you get 12 million bits, 12 million bytes actually. Too big. That's what a TIFF format is. It's raw format. It's too big. So what you're going to do is you're going to compress it. We use source coding. We use source coding to figure out what are the most common elements, and then we shrink it down, and that's what a JPEG is. JPEG is just a way of doing a two-dimensional discrete Fourier transform on the image, and this allows us to essentially remove all the extraneous elements, but I won't go into that. Okay, so that's quantization. That's really all I wanted to say about it, and you probably know quite a bit more already, so I'm not going to talk too much about it. Now we're going to focus attention on the following thing, which is that I've given you a sequence of bits, and I want to send them on a channel, on a channel which is not digital, but it's actually continuous. Because in reality, all channels are continuous. We really don't have digital channels ever. Even if I'm sending single photons on a fiber optic cable, the photon receptor is an analog system. Okay, so at the end, it's all analog anyway. So we're going to now see how we convert an analog channel into a digital channel. Okay, so just stepping back a bit, when I first drew that picture of the source, the coder, etc., I started with the digital source, and now I've shown how you can take an analog source and make it digital. And then I assumed it's a digital channel. Now we're going to consider how to take an analog channel and make it digital. Okay, so I need a couple of results from hypergeometry. Actually, first I want to show you how we represent this. Let's just forget this for a moment and focus purely on the 1D, one-dimensional case. So it's just sufficient. So we basically say that each of these over here, we'll call that x sub I. So we have a sequence of values x1, x2, x3, etc., xn, and that's the time series of binary values that are binary symbol sequences that are coming out of here. So for example, x1 could be 0001, could be 1001, whatever. So we have some sequence like this, okay? I'm going to focus on a block of n values, okay? It's a block of n values, I'll just call it a block, okay? And so the block of values can be viewed like this. I can, let's say I have a block of 3 values, okay? So x1, x2, x3. All right. Now, I can view this block of 3 values as being a point in 3-dimensional space where I have this axis, for example, to be the x1, actually say capital X1 axis, capital X2 axis, capital X3 axis, where x1, x2, x3, the capital ones are the random variables, and these are the domains. And so x sub 1, the small x1, is going to be some value over here. Let's say this is 0, 0, 0, 0, 0, 1. Okay, let's say this is 0, 0, 1, 0, 1, 0, 0, 1, 0. So this is 0, 0, 1. Let's say this is 0, 1, 0, and this is 0, 1, 0. So somewhere in space over here, which I can't quite draw, okay, right here in space is that signal point. Okay, as you can see, each and every possible signal sequence like this, x1, x2, x3, corresponds to a point in 3-dimensional space. Okay, right? So generalizing from this, if I have n in my block, I have n elements x1 to xn, then this corresponds to a point in n-dimensional space. And from our perspective, we can't really imagine anything beyond 3 dimensions. If you stretch your brain, you can do 4, but 15 dimensions, we don't really know what it means. But don't worry, all we mean is that each point in that 15-dimensional space corresponds to 15 values. Okay, that's it. I can pick a point and say, yeah, that's a point. That's if there's 15 values corresponding to it. So you can say each point in the space is a tuple x1, x2, all the way up to x15. That's a point in 15-dimensional space, and that's relatively easy to understand. We need just one result, only one result for hypergeometry. Okay, so first of all, actually I should tell you 2 results. I'm just going to write this down. First, the energy of a point x1, xn is defined to be sigma xi squared. Okay, we define that to be the energy, and the reason why we define that to be the energy is basically because we, intuitively speaking, if you think of this as a voltage, let's say this is a voltage over here, V, we know that the electrical energy is V times I is the electrical energy, okay, which is nothing more than V squared by R, where R is some constant. Okay, so if I have electric current flowing in a circuit, the energy is VI. Okay, so V squared by R. So the energy is proportional to V squared, where V is the signal amplitude of voltage. So intuitively, it kind of makes sense for us to say, well, if you think of these as voltages, okay, then the energy is corresponding to the square rather than the sum. Okay, so sigma xi square is the energy that corresponds to this. So more pragmatically, it's like this. Let us say that I have a cell phone, and the cell phone is sending out the signal over here with these voltages. The amount of battery consumed, the energy consumed from the battery, is going to be sum of the VI square. So if I have large signal amplitudes over here, I'm going to actually end up with large amount of battery being consumed. Yeah?
Shouldn't it be called power? Because if this is independent of time, how can energy be independent of time?
So you can think of it as the amount of energy consumed in this time period t. So there is an intrinsic time period of t, which is the sampling into. So yes, you're right. You can think of it as it's not actually the power; it is the actual energy. Okay. All right. Okay. So the energy of a point is considered to be this. That's the first fact, and the second fact we have over here is that the volume of a sphere sorry, I should probably be careful, of an n-dimensional sphere with radius r equals r to the n. Okay, so small n. So that's it. So I should not say equal to, I should say proportional to. Like, so for example, if you have volume of a sphere, it's 4 upon 3 pi r cubed. So it's r cubed, so it's proportional to r cubed. The area of a 2-dimensional sphere is sort of the volume is pi r square. The length of a line is r, right, proportional to r. And if you go into 10 dimensions, or the 15 dimensions we have over here, the volume is r to the 15, whatever r is. Okay. There's one consequence which is not obvious, but it's kind of fascinating to think about. So let us say I have a hypersphere. I'm just going to draw it like a circle, and I look at the radius r, okay, and then I look at another sort of internal sphere which has a radius of 0.9 r, let us say. Okay, so I'm looking at 90% sphere, 90% size, and I'm going to ask you the question: what fraction of the volume of the sphere is close to the surface? Okay, well, the volume of the volume of this sphere is going to be r to the n, and the volume of that sphere is basically going to be 0.9 r to the n. So it's basically r to the n into 1 minus 0.9 to the n. Okay, so this is the amount of volume which is within 10% of the surface. Okay, within 10% of the surface. So as n goes to infinity, this value goes to basically 1. All right. So as the dimensionality of the sphere increases, okay, what happens is more and more of the volume is near the surface. Okay, it's sort of a bizarre thing to think about, but that's what's going on. And you can think of it as something like, as the dimensionality increases, it becomes sort of like a hollow sphere. Okay, so if you have a 100-dimensional sphere, almost all the volume is very, very close to the surface. Okay, so if I take a point at random in that sphere, very likely it's on the surface. Okay, and there is no real easy way to think about it other than to say it follows from the math. Okay, the other way of thinking about it, the easiest way I can think about it is to say, well, if you take a sphere, a three-dimensional sphere of unit volume size, okay, then the volume is 4/3 pi, and then if I take a unit of size half, then it's going to be 4/3 times pi times 1/8, because it's half to the cube. So 7/8 of the volume of a three-dimensional sphere is in 50% on the outside ring. So we have sort of this inner ring, which is 1/8, and then 7/8 is sort of on the is in the remaining 50% radius. Okay, and with a n-dimensional sphere, nearly everything is sort of on the outside edge. Okay, so a point like this, x1, x2, x3, in an n-dimensional, so a signal point like this is almost surely on the surface of the hypersphere. Okay, from here. That's what we get from here. So that just comes from this result directly. Okay, so with these two results, we are now more or less able to compute the capacity of a Gaussian channel. Okay, so this result and the energy of a point. So basically what the energy of a point equal to sigma xi square says that a point that is on the surface of an n-dimensional hypersphere of degree n is going to have energy corresponding to this. Yeah?
What does it say over there? The radius is r.
The radius is proportional to r over n.
Oh, it's out.
Sorry. Radius r is proportional to r over r to the power n. Okay, so I'm going to now talk about a Gaussian channel. What does it mean to have a Gaussian channel exactly? A Gaussian channel is a model of a real channel. Okay, so what happens in a real channel is that we're going to send an analog voltage on it, right? And on the other side, we're going to get that voltage plus it's going to be distorted, and the distortion is called noise. So let's look at it this way. I'm going to consider a very simple channel where this is the time instant 1, time instant 2, time instant 3, just looking at 4 time instants, and it has some voltage level. And just to make life really simple, I'm going to say that the voltage level, let's say 5 volts corresponds to 1, and 0 volts corresponds to 0. And I want to send the signal sequence 0, 0, 1, 0. Okay, so it's going to be 0, 0, and it's 1, and then 0. Okay, so that's my signal, and I've drawn that with the X marks over here. So basically, at the receiver, what I'd like to see, if it was a noiseless channel, are the signal voltages 0, 0, 1, 0. A noisy channel is going to add some noise to it. So let's say that the noise is typically symmetric, it could be positive or negative. So this green shows the noise, and so here are the noises over here. And let's say I have some noise like this, okay? And actually, let me change that noise because I want it to do something for me. I'm going to put the noise to be positive again, okay? All right, so this is what the noise looked like. So one could ask, what does the noise look like? What are these green lines coming from? And we could say, well, let's say this is noise N1, N2, N3, N4. Certainly, these 4 noise values could be thought of as being drawn from some random, as being values assumed by a random variable capital N, right? That's a noise distribution, and we could characterize the noise distribution empirically by measuring the noise values, right? Because we know what we sent, we know what we received, the difference is the noise. We can characterize what N is, and we have the probability mass function of N, and if we have sufficiently large values, we can model it as a continuous distribution, right? In the same way that we can take a series of discrete values and fit a Gaussian to it, in the same way we can fit something to it. And a typical description of N is that it is independent So the noise values are independent of each other. They're additive. Okay, and they're drawn from a Gaussian distribution. In other words, the actual amplitude over here is given by the Gaussian formula. Okay, 1 upon sigma root 2 pi, whatever e to the minus x minus mu by sigma square. So that's the Gaussian distribution. So this independent means that when the noise value here and the noise value here, if I know the first noise value, I don't know anything for the second noise value. This is actually almost never true in practice. Almost never true. The reason is because the sources of noise are things like, in electrical systems, are noise like drills, lightning strikes, okay, things like that. So if somebody turns on the vacuum cleaner, you get noise. If you're sending a Wi-Fi signal, somebody turns on the microwave oven, you get noise, okay. The microwave oven is on for a long period of time, so you get noise that's correlated. If the noise is high, it's going to be high again, right. So in practice, noise is almost never independent. But again, for the sake of mathematical analysis, we're going to assume here the independent. This means additive. What does additive mean? What this means is the received signal, which I'm going to show with orange, is the sent signal plus the noise. So it's going to be this one over here. Here it's going to be this one because there's zeros. Here add this and this to get this value over here. And here add this and this to get this value over there, right? So the orange lines represent the fact that the noise is additive, okay? And the independent in the joint from Gaussian distribution. Typically, the independent is also written as white noise. So this is another way of calling it as white noise. And so this is usually summarized as AWGN, additive white Gaussian noise. And if they're dependent, it's often called colored noise or pink noise, which means that there's some independence. So there's dependence between the values. Again, so we can look at what's called the autocorrelation function, etc., but I'm not going to go into that. So we're going to assume that the noise follows AWGN, additive white Gaussian noise, and it will become clear why we need this, because it simplifies our analysis tremendously. Okay. So to come back to this, what does the receiver see? Well, the receiver sees over here, this orange thing over here, and says, well, let's say that anything about this dashed line is considered to be a 1, okay? So I'm going to mess with that for a moment. I'm going to make the noise higher. There. So this is going to be my threshold, okay? And anything below that, I'll just say it's a 0, because I'm going to get variable values. I need to make some decision, so I call that over there. So this one, the receiver says, I think I got a 0. So it's going to say, so orange is what it receives. So I think I got a 0. Here it says, yeah, I think I got a 0 because it's really below that threshold. That's 0. Here it says I got a 1, and here it says I got a 1. Okay. So the transmitted signal was 0010. And the received signal, the digital signal, was 0011. Why did we have this received signal? It's because this particular noise value was so large, right, that the threshold was crossed. Okay. How could we have avoided it? Well, what we could have done was that if the noise is going to have some distribution, let's say the mean noise value is something and some standard deviation is there, if you'd chosen this to be, instead of 5 volts, let's say it was 15 volts way up there, okay, so the plus, we were sending a dash and the threshold was set over here. If we set that threshold, the noise would not have affected us, because the noise is kind of doing something like this and way up there. It's not really affecting us at all. It's never going to affect us, right? So the intuitive lesson from this is that if the signal values are sufficiently large, okay, the signal value is sufficiently large, then what's going to happen is that we're not going to have any effect of noise. Okay, even though the noise is there, it's not affecting us. We're not going to make wrong decisions. In fact, we would get the output as being 0010 despite the noise. So given a particular noise value, what I can think of is if I boost the signal strength sufficiently, okay, I can get rid of noise. And that is the basis of digital transmission. Okay, digital transmission says, I'm going to restrict my alphabet to just zeros and ones, but I'm going to choose the signal strength sufficiently high so that the noise doesn't affect me. And that's what happens on CDs. Okay, you know what, a CD is just a thin film of aluminum, okay, like the same kind of aluminum that you use for wrapping your sandwiches, the same kind of aluminum on which they made little holes. If there's a hole, it means that there's a bit. If there's no hole, it doesn't. So you shine a laser on it, and either it reflects back to you, so you put a detector. If it reflects back to you, there wasn't a hole. If it doesn't reflect back, there was a hole. So the detector just goes, yeah, hole, no hole, gets zeros and ones, right? And that's it. Okay? So if you scratch a CD, what happens is that you're going to get some bad reflections, so you're going to make a mistake. But because we can deal with that noise using coding, in practice, you never see the noise. Okay? That's why CD sounds good, even though it's scratched, up to some limit. Okay? Once the noise amplitude goes above the threshold, we're going to be in trouble. Okay? That's the digital channel here. Okay, so the effect of noise, effect of additive Gaussian noise is to do this. So let's just pause for a moment and say, what would happen if there were no noise? Okay, just for a moment, we have this fantasy universe, there's no noise. What's going to happen is this: if I send a signal, okay, what is received is going to be exactly what you sent. Okay, each signal actually is a real number. Okay, it's a voltage, it's a continuous quantity. If I could send that voltage across to the other side with no distortion, no noise whatsoever, a real number has actually infinite capacity because it has infinite precision. Right? So if I send you some real number and I had a detector which had infinite precision, I could send you essentially at an infinite information rate. Because I could send you gigabits with just one signal, because it's all encoded in that real number. Okay? So in this fantasy world where we have no noise, even one transmission is enough to transmit everything that you ever wanted to transmit. Right? So you want to download a movie, it sends one real number, and in the millionth bit it tells you, actually the billionth bit has the last information that you need for the movie. 1 gigabit can be sent with just one signal. Okay? Unfortunately, this doesn't exist. Okay? Unfortunately, what happens is that if you want to go beyond a certain level in terms of your signal precision, noise comes into the picture. So noise cannot be removed. Okay? So that is again Shannon's contribution. Shannon basically said, look, we don't have this fantasy world where a single real number is enough to transmit everything. We do have to worry about noise and noise amplitude. And the way we get around noise amplitude is to basically boost the signal. Okay? Okay, any questions about this so far? Okay, so what have we studied so far is we can take a continuous signal, we can make it digital, great. These signals correspond to points on the surface of a hypersphere. Okay? Now we are moving from the signal to the channel. We're saying the channel actually looks like this, but we're going to take the continuous channel and make it look like it's a digital channel by choosing these voltage values and choosing a threshold. And for the sake of modeling, we'll assume that the noise values are independent, additive, and drawn from a Gaussian distribution, the so-called additive white Gaussian noise model. Okay? Any questions about this so far? Okay, so given this, we can now start computing the capacity of this additive white Gaussian noise channel. And actually, before I do that, I guess I had one problem set, which was what is the energy corresponding to the signal? And the energy corresponding to the signal was basically the signal was I'll just write it out as numbers is 3, 3, 3, 3, 2, 3, 4, 3, and so the squares are 9, 9, 9, 9, 4, 9, 16, 9, and so the energy corresponding to this is 74. Okay, in what appropriate units? Which so the sum sigma xi squared, so that's the value that we have over here, the energy. Okay, so that was easy. Let's now move on to the capacity. Yeah?
Earlier you had told while choosing this binary digits,
Yeah.
according to our
Right.
In that case, with the choice of our binary digits, the energy changes, right?
That's correct. So you're right. So I was being somewhat imprecise over here. So remember the analog signal is at the message source side. Once we choose the digitization values, that's the source coding, right? That's the source coding I'm talking about, the energy of the source code. I can do a channel code as well. The channel code can transform some values to other values, and then I can make it lower energy if I want to. Okay. So I'll choose the channel code to be not just lower energy, but also